Yeah, so there's so sigma y is 0, sigma x or sigma z actually is 0.
And then sigma x.
Yeah.
1 and 3 is basically 3 points.
Yeah. 3 was nice.
2 is okay, but 1, 2, 3 is good. I guess we'll just have to see. I guess we will see. Today at least it's over.
I know, right?
Say hi. Check. Can you hear me?
He has another exam and like a quiz.
I was gonna have another exam today, but because of DSS scheduling stuff, I couldn't, so I had to get
Say something. Do you have audio?
He has another exam. He had 2 exams and a quiz today. I had 2 quizzes and an exam.
Yeah, I can hear you.
Okay, got it.
Oh yeah, we can
Oh yeah, you're in my section. I sit in the front, so I probably didn't see you.
I sit in the very front and the left. Well, no, not very front rows. Yeah, front on the left.
I'm gonna start in the front on the aisle.
On the right. Yeah.
Okay, looks like one question
Did I know you were in my
today.
section? Actually, I probably did at one point, but I forgot.
You did once.
I definitely know you're in my section for arrow. I definitely know you're in my section for arrow. It's like, oh, we sit right next to each other and we're in a group. Who would have thunk?
Did you have exam or something?
Structures on the Dr. Rad.
Oh.
And I had 2 other quizzes today.
Oh my God. Structure. I mean, everything's algebraic. It's nothing bill against bill. No, I'm just kidding. I have to study. Yeah, go ahead.
What's your favorite color?
Huh?
What's your favorite color?
It is algebraic, but when you get a whole calculation, there's a negative sign because a stress component is positive and
I don't differentiate.
And you get the wrong principal stresses as a result of that. And then you get sigma von Mises wrong. And then you get sigma fracture wrong. And then you get basically
Okay.
You might
Ian,
say
Michael.
that's like carry over.
So, did you get my email?
Yes, I
What do you
did.
think?
I'm up for it if everyone else is up for it. I think that's a great idea.
Do you want to do it?
If everyone else is okay with it,
Do you want to do it? What do you think about that?
I've talked with Steve more about it.
I mean, it looks like he might be
Steven's
doing a
already doing
special project.
So basically 2 and 2. So you can form one team, another team if you want. Ian, do you want to form a team with it?
I still haven't learned about it from Steve, so.
Okay, well,
I can
yeah.
toss them after slash.
You can form like a four-person team if you want to,
Yeah, it's the three
because
of
you
us
are an
and then
SAE
someone
anyway.
else.
Do you want to do that?
No, there's 3 of us and someone else. There's 4 people. I just don't know the 4.
Yeah, I need a response by probably this week.
Okay.
So think about it. Okay, so let's just take in-class attendance. Okay. Okay, let's just get ready for in-class attendance. Okay,
I know. When you said you could do that, first thing I thought I was just like, no. I feel really badly about it.
No, I'm not gonna lie. When I got that email and they told me that you're not, I'm thinking, no,
So yeah, so for one essay,
oh, I first okay, you're in
so
the
yeah, so what I'm gonna be doing
my first thought was, dang it, I'm ditching the group. I've gotten ditched like 3 times and now I'm doing it to other people.
attendance done. Good.
That's all good.
Yeah, no, it's fine. No hard feelings.
Hopefully it goes through. Then maybe I'll see you in the lab.
Oh, wait, do you use the ACSL?
Yeah, well, I will. He did the thing to get his taxes, but I don't have it yet. I'm trying like twice today.
I think he's in the process of doing it for our group as well. So eventually,
Some
probably
programs
by
I
the end
have
of it.
it, like Steven.
He's been in the club since last year. Me and Michael just
All right, everyone, let's
we
just
can work
get
on
started
future
today.
projects together. We
Okay.
got more than one group project in this course.
So today I'm going to conclude Unit A3 by discussing a little bit more about the Bernoulli's principle. No, I'm not talking about Bernoulli's equation. I'm talking about Bernoulli's principle. It's not one equation. you are seeing the series of similar kind of equation, algebraic form you can apply for aerodynamics, for low speed and high speed. Those are all based on Bernoulli's principle. Okay, so let's just take one more look at it. Okay, and then understanding is the key. Like I said, this is not the class anymore, plug and chug. So understanding Bernoulli's principle hopefully help you sort of plot what is the story behind all of those equations. Okay, so you're believing that Bernoulli's equation is coming from conservation of linear momentum going through Euler's equation with assumption of density constant. Now I got Bernoulli's equation. That's not true. Well, that's one way of getting it, but that's not the whole story. So let's just discover those things today, okay? And then I have to tell you, those are the questions that I really want to answer. No, I really want to have. Well, those are the questions I love. Period. You can interpret in any way you want. I'm not interested in plug and chug capability of anybody. I'm interested in your understanding of the basic concept. So I try to do my best to design the exam to capture that portion. It's not plug and chug. Okay. All right. So anyways, so today the last page of Unit A3, summary of equations. Of course, you have two sets of equations. One is equations you can apply only for low speed. Less than 0.3 Mach number is, of course, you can tell density is constant, yes. But one more thing, you just completely ignoring one more thing. What is it?
Mach number.
Mach number is less than 0.3, you know that.
Continuity.
Internal energy.
That's right. That means you're completely ignoring the temperature variation within the flow field. So low speed, this means literally isothermal flow field. Temperature never change. You don't even talk about temperature change. That means you don't even talk about fast law of thermodynamics at all. This is not energy at all. It's just a momentum. That's what you are talking about. Okay? And then you realize that, hey, this is the momentum equation, right? Yeah, that's right. But is it really? Okay? So that actually reinforces your understanding of quiz 3. And then quiz 0 problem 3. You went through wind tunnel testing. Then you thought you applied Bernoulli's equation, but it's not. You actually applied energy equation for it. Okay? So if the Mach number becomes more than 0.3 Mach number, that means one thing you have to incorporate within. That one thing is, of course, not the density change, no. It is it's energy. In other words, this kind of work starts to come in, okay? That actually creates the work, energy transfer. So you have to incorporate the energy balance, one more term in it. Density is now variable. That means specific volume keeps changing. Density, of course, changes, but it's not the direct thing. It's like a specific volume keeps changing. That's why, as a result, density needs to be variable. Okay, and what is the bottom line? Well, you have to take a look at work, energy transfer, which is faster of thermodynamics. Energy still needs to be in balance. That's something you have to incorporate. So you come up with, instead of Bernoulli, you come up with something called energy equation because you use the energy principle. That's why this is called energy equation. But is it energy equation? Energy equation. Okay? Then obviously, continuity, you have to deal with the density, which is variable. Density cannot be constant anymore. And also, if you look at the two locations, 1 and 2, okay, you can still relate the pressure, density, and temperature between two locations. Isentropic. Okay. So that is a summary. Okay. Now here's the important thing. Okay. I think I saw the important thing. Something is written here. Okay. Somebody already know this is not energy. Well, this is energy equation, but this is, by the way, you can still call this Bernoulli's. It's just Bernoulli's principle-based equation under different conditions. Okay? That's what it is. So let's understand that more appropriate manner. So I want to take a look at, let's just introduce Arnie, the engineer board. Okay? So Arnie is going to challenge you, hey, let's understand more about Bernoulli's equation. Actually, I'm not even talking about Bernoulli's equation. I'm talking about Bernoulli's fundamental principle. What is that? So if you're talking about raw speed, raw speed. What is raw speed? Anyway? What makes it raw speed? Yes.
So like what's the Mach 0.3? Is that?
Mach number 0.3 or less is the raw speed you say, and then we haven't even discussed about why. People say that all the time. But based on what discussion you say that, well, we're going to find out, hopefully. Okay, I don't expect your answer right here, right now, but hopefully you're going to find out that answer by the end of Unit A4, okay? So stay focused on it. But somebody said 0.3 is a cutting line, okay? Sure. So suppose if you're talking about raw speed, what's exactly happening? This is Bernoulli's equation. Now you casually pick up this equation coming from fluid mechanics and then use it for the flow field just like this. You know, remember quiz 0 problem 4. That's right. Did you do that? Okay, so when you try to solve the quiz 0 problem 4, this is the only equation you probably had from fluid mechanics. So you apply this, and then, whoa. Right here, Mach number is really less than 0.3, but right here, 0.3 something. Oh my goodness, how am I doing right there? Question mark, big question mark, big question mark. Because this is the only equation you know. And then remember also quiz 0 problem 3 and also quiz 3. That is wind tunnel, raw speed. Okay? So this is the equation you picked up. You apply this equation along any location, the streamline, and then remember wind tunnel test section, okay, where the velocity is v. That means you're creating the dynamic pressure Q. This is Q, by the way. So this plus that must be equal to 0 all the way through. At the stagnation point, velocity is 0. This is 0. Pressure 2 also must be 0. 0 plus 0 is 0. So if this is Q, what is the P1 equal to? Of course, minus Q. Then I made a comment saying, oh, that's a trade-off. Trade-off between kinetic energy and flow energy. What is the flow energy? This is the energy content you need to make the flow field move in. So any moving fluid, you need to have a flow energy. So in this case, density is constant. In other words, this is not a variable. So only way to increase this velocity is decrease this pressure. So it's a trade-off of those two energy contents to create, if you add them up, it's going to be always constant value, right? So if the flow is not moving, this is 0. Pressure is certain value. If the flow is moving, pressure needs to be decreased. Okay. That's what you apply to solve quiz 3 and also quiz problem 3. I hope you understand that now, okay? And then if you come to think about, if you start up from this Bernoulli's equation of aerodynamics, one term is already missing from fluid mechanics. What is that term?
Hydrostatic pressure.
Hydrostatic pressure variation here and here, gamma times Z1, gamma times Z2 is already missing. Why is that? Why?
We're assuming the same,
It's in
same
elevation.
Z line.
Eh?
Same Z line, or same elevation.
Well, you can say same elevation, but suppose the elevation is like this, do you still drop it?
Ignoring gravity.
Ignoring gravity, that means gamma of air is so low value. So let's assume it's close to 0. This is aerodynamics assumption, 0 gravity or no body force assumption. Do you remember that?
Yeah.
I hope so. That's why gamma z term is not even in the equation itself. I don't even apply it. You can say it's the same height, but still, if the height is different, I don't care. This is aerodynamics. That's why I completely ignore that term to begin with. So this is aerodynamics term, 0 gravity or no body force version of Bernoulli's equation. Is that correct? Okay. So let's assume density constant. Let's divide both sides by the constant density. Then now you realize, wait a second. This is something called flow energy. This is something called kinetic energy. Flow energy and kinetic energy is constant along the given streamline. What kind of principle you're talking about?
Conservation of energy.
Conservation of what?
What do you remember?
Conservation of what?
Energy.
Energy. First law of thermodynamics you're talking about. Okay? This is the conservation of energy. Question, go ahead.
Did you say you dropped the gamma z because gravity is 0?
I said that.
I'm making sure.
Didn't I say that? I said
I didn't understand it.
Why is it that? Because how heavy your air?
Oh, okay.
Yeah. I don't care, right? Okay, that's one. So knowing this is first law of thermodynamics, I want to describe a little bit more. Well, this is the complete form of energy. If you're talking about energy contents, didn't you take some? What kind of energy creates the total energy? Well, one is internal energy, one is kinetic energy, one is potential energy, one is also flow energy. If it's moving fluid, okay? If it's moving fluid, you have four different kind of energy. One is internal energy, one is flow energy, one is kinetic energy, one is potential energy. Now, potential energy is already dropped off from aerodynamics. You know why? You know why?
Body force.
You know why? I want to hear from you. You know why? Why? Why this is dropped off? Tell me. Tell me. Why? Yeah, I want to hear you.
Why did it drop down? Gravity is 0.
Why this is dropped off? Why?
No body force.
Why nobody force?
It's-
Because air is so lightweight.
Yeah.
Gravity's effect is completely ignored. This is aerodynamics. Do you think today's air is so heavy? No, I don't feel anything. I don't care about gravity effects on flow field. That's why, okay? So this is the fundamentally aerodynamics assumption, okay? Something's added. What did I add? That means we have been completely ignoring for such a long time in Bernoulli's equation. Well, I added this one, and also I added this one. Why did I need to add? Because the temperature may be at different values. Internal energy may change in high speed. Also, density is now variable. Density here, density there could be different value. That's fine. This is the complete description of the first law of thermodynamics applied between location 1 and 2 in high speed. Okay? And then, of course, those two are dropped off. And then you can combine those two, right? What is it? This is called enthalpy. This is called enthalpy. Now, suppose if this is canonically perfect ideal gas, what is H? CPT. CPT, voila. You got energy equation. So what did you do? Is this still called energy equation? This is Bernoulli. What are you talking about? Right? So I'm seeing the variations of Bernoulli's principle-based equations from low speed to high speed. That's what we are seeing here. You get that?
Yeah.
So that means, starting from here, can you get Bernoulli's equation for less than 0.3 incompressible Mach number equation? Of course, you can do it. Now, starting from Bernoulli's equation less than 0.3 Mach number, can you get this equation? You can do it. I'm doing it right here. You can switch back and forth, back and forth, back and forth, back and forth, based on the conditions you specify. You are looking at the same old thing, Bernoulli's principle. That's what it is. Okay? So this is the difference between low speed and high speed. Okay? So this is the streamline between location 1 and 2. If this is low speed, density is constant. Also, at the same time, you inherently kind of assume already temperature never changes. What are you talking about? I don't even talk about the temperature. Isothermal already. That's why the pressure and velocity are coupled. If you know pressure, you can get velocity. If you know velocity, you can get pressure. That's pressure-velocity coupling equation. That's the low speed. So when you do low speed testing, you're going to measure pressure, nothing else, right? What kind of device are you going to use? Manometer. That's low speed testing. So what about high speed? Okay. Now, high speed. Condition is, well, density can change as long as you keep track of the temperature variation. So this equation basically says the temperature and velocity are related. Temperature, velocity coupling. If you're given temperature information, you can determine velocity information. If you know the velocity information, you can determine temperature information. Based off of that, if the flow is isentropic, you can get pressure, density, temperature. So the assumption is this can be more than 0.3. That means density can be a variable. However, at the same time, flow field must be isentropic. In other words, very simple external aerodynamics. You cannot have combustion chamber, some kind of weird thing that you keep adding the heat energy into it. You can never handle such a thing. And also, flow across shock wave, flow within boundary layer, flow highly turbulent. Those are all reversible. That means it's not isentropic at all. You can never apply this kind of equation for such a situation. So this is limited, of course. However, it's no longer limited for 0.39. Okay. And then gas must be perfect gas. Obviously, if you're not talking about really high temperature, gas behaves perfect gas somehow. It could be calorically perfect ideal gas in room temperature range, or it could be higher temperature zone. It's going to be thermally perfect, but still ideal gas. Then you can use this equation. Okay. So I hope you really understand this. This is the most important thing. I don't care if you can put the plug and check. So selection of the equation and then knowing the limit of how to use that equation is the key. Unless you do that, I'm not convinced that you understand this. Bernoulli's principle. This is Bernoulli's principle. Okay? Now, Bernoulli's principle, once you understand everything, probably start like making sense. In other words, so I hope you're doing quiz 4, okay? And then get ready for quiz 5. What is a quiz 5? Based on quiz 0, problem 5. Have you looked at it? Quiz 0, problem 5.
Manometry.
Well, it's not manometry. It's speed measurement. Speed measurement. So take a look at 3 equations. I just wrote it down from fluid mechanics. What are those 3 equations, anybody? Go ahead. Those are, which one's Bernoulli?
Well, they're all different forms of Bernoulli.
Those are all different forms of Bernoulli. So this is the Bernoulli's equation, something called pressure conservation form. Pressure is constant for a given streamline between location 1 and 2. 3 types of pressures, if they add it together, it's called the total pressure, which is constant, which is quiz 3. Okay? Static pressure, what's that?
Dynamic pressure.
Dynamic pressure, what's that?
Hydrostatic.
Hydrostatic pressure. Those 3 added together is called total pressure. P0. And then quiz 3, what is the total pressure value in terms of gauge? 0. That's what you did. Now, suppose if you divide this equation by constant density rho. Now, in fluid mechanics, oftentimes density is constant. Okay? What's this?
Flow energy.
This is flow energy. What's this?
Kinetic energy.
Kinetic energy. What's this?
Potential.
Potential energy. So added together as total energy of a moving fluid. Although you're completely ignoring the internal energy. Internal energy, of course, it's same. That's your energy. But total energy is constant throughout streamline. Okay? Added together is total energy. Have you ever seen it?
You divide by gravity.
Divided by gravity, that's why. What's this?
That's
What do you call that?
specifically.
No. What's that? Did you actually take the fluid mechanics?
Yeah.
So you know that equation. What is it? Eh? So this is pressure. This is energy. What's that?
Work.
No. You guys don't know this.
I remember it. Just got
What's that?
name.
This is called head.
Oh.
Hit. Remember the pipe flow? What is that? What kind of head?
Pressure head.
This is called static head. Static head. What is the static head of this cluster right now? Roughly speaking. Well, 750 millimeter HG, what do you mean? If this is a 750 millimeter of HG, how do you convert it to P1? Multiplied by rho G of HG. Gravity of Earth, rho of HG. If you multiply those two to the 750 millimeter, you get pressure. What do you call that? Static pressure head. Can you convert such a thing? Millimeter Hg converted to PSI. How would you do that? Multiply by rho G of whatever the liquid you're talking about. If it's Hg, multiply by rho of H. If you're talking about water, rho of water. Okay? Are you listening? And this is very important for quiz following. If you want to go somewhere, please go ahead. Because you're going to screw up quiz following. What's this?
It's dynamic head.
Dynamic head. 10 inches of water. What do you mean? Oh, you walk into the wind tunnel. How fast this wind tunnel can go? Oh, 5 inches of water. Huh? What do you mean? That's the quiz file. Did you look at it?
Yeah.
Quiz 0, problem 5. Did you look at it? That's what this is. Okay? Now you can solve it, right? What's this? It's just a height. It's a head. Height. Head means if you have a pipe and liquid within, if you pump in the pressure this much, how much height you can achieve. That's called head. This is head. Static pressure head. Dynamic pressure head. Head. 5 inches of water. That's what that wind tunnel can go. Okay. Now you can convert it to velocity, right? What kind of information do you need? Of course, gravity, you need that. And
Density of the fluid.
density of fluid and density of air, both you need. Then you can convert it to airspeed. Okay, so people don't talk about airspeed 50 miles per hour for wind tunnel. They always talk about inches of water. You have to find out why. That's the next quiz. So let's just take a look at quiz 0, problem 5. Okay, well, by the way, any question here? I'm going to conclude Bernoulli's principle. This is important. Okay, go ahead.
Just to be very clear, what was the third one again? Or
What's the third one? Huh?
top equation?
Top equation of what?
Omega Z.
Wait.
This?
This?
Yeah.
This?
Yeah.
This is hydrostatic pressure.
Interesting.
In aero, we completely ignore it. Okay? Because gamma of air is so raw. Okay. So this is something you need to understand completely now. Okay. If you feel uncomfortable, talk to me. Really, seriously. If you leave this kind of thing behind, you can never pass this class. I'm not going to allow you to pass this class. Okay. If you feel uncomfortable, feel like I don't understand it, please talk to me. I'll walk you through it personally. Okay. This is so important. If you have no clue about this, no, you cannot move on. Okay, so let's just take a look at, okay, quiz 0 once again. Quiz 0, problem 5. Where's quiz 0? Oh, yeah. I hope you continue working on those quiz problems. Quiz 3 is done. Quiz 4, you're working on it. Quiz 5. Here we go. So this shows up airspeed measurement. Of course, we are going to get into unit A for today, airspeed measurement. But let's just take a look at it. This is basically 100% based on the fluid mechanics idea. That's something we talked about today. Okay, the third equation: static pressure head, dynamic pressure head, and head. Total head is constant. And then if you're talking about dynamic pressure head and wind tunnel, people talk about Oh, 5 inches water. Here we go. Okay? Here is the actual photo taken at the ERAU wind tunnel laboratory because I took the photo by myself. Apparently, this wind tunnel is equipped with a custom designed inclined U-tube manometer for the test section airspeed measurement. Do you guys know inclined U-tube manometer from fluid mechanics?
Yes.
Of course you know. There's only one thing you can measure from this device. What is one thing you can measure from this device? One thing only, nothing else. Pressure, not the pressure. No, pressure difference.
Thank you.
That's the only thing you can determine. Pressure difference between where to where? From here to here. One tube is connected to somewhere. The other tube is connected to somewhere else. This device can pick up only the pressure difference between those two spots. Where are those two? We're going to cover that, okay, in Unit A4. Don't miss it. Anyways, it looks like the manometer is in terms of inches of water. Huh? It's like, right? And the maximum measurable value is about 5 inches. It looks like, okay, 1, 2, 3. This is 5. This is 5. So this is about 6 inches. By the way, which side is a high pressure end? Which side is a low pressure end?
Low
Anyway.
pressure should be on the left. Left side should be-
Left side is a high pressure. In other words, liquid is pushed down and pushed up. And then you're supposed to measure this much distance. This much distance is inches of water. Okay, anyways. A, explain the meaning of inches of water. Please try to explain with your own word. Please convince me. I can easily tell if you understand or you have no clue by reading your statements. Okay. What does inches of water represent for wind tunnel testing? Of course, how fast this can go, obviously, but don't you want miles per hour for it? But people never tell you miles per hour. Why is that? Why do we need to employ such a thing for wind tunnel testing? You have to find out all of those answers. Best place to start is Bernoulli's equation, third form, head equation. That's where you begin. Okay? Suppose if air density in this wind tunnel test section is given, say 0.002 slides per cubic foot, what would be the corresponding wind tunnel test section airspeed in miles per hour for the 5.7 inches of water reading of this manometer? Gravity is given, density of water is given, unit conversion is given. Somebody please tell me what's your value. Anybody who actually got it right value? Please don't hesitate. Raise your hand and tell me. Oh, I got the right value. 100 some miles per hour, right? I believe. I don't know my number, but did you look at it? Have you ever looked at it? Are you ready to go for next semester wind tunnel testing? If you don't even know how to convert inches of water, how can you use that wind tunnel testing device? You have to figure out. Somebody actually got the right value? Don't hesitate, don't hesitate. What did you get? What did you get?
117.
What?
117.
117. How did you get that?
I
Can you explain that? Question is. It's not plug and check, right? You know exactly what you're doing, and then I got this value. That's what I want. If the equation is given plug and check, I got 117. Well, anybody can do that. I'm not interested. So again, question is correct.
I think like I used the Bernoulli's equation and then did pressure difference.
Doesn't make any sense. Bernoulli's equation, right? But why this is inches of water? Question for you. Do you think this is water?
No.
No. Do you think this is actual inch?
No.
No. No. It's inches of water. Somebody designed the angle and the liquid of choice to make it inches of water. It's not the water. It's not the actual inch. It's inches of water measurement. Measurement of what? It's a dynamic pressure head that this wind tunnel can produce. That is, happen to be 5.7 inches of water. So how much actual pressure are you talking about? And then that pressure is a dynamic pressure, 1/2 rho v squared. Right? That rho is an air rho. So So square root of 2 times that dynamic pressure divided by rho of air is going to get you velocity in miles per hour. So do you understand those things? So you have to think about it, okay? So anyways, let's just go into the unit A4, airspeed measurement. This is a new unit, okay? So as we move into unit A4 today, let's just take another look of first of all, speed of sound, because we all know the speed of sound equation. What is it? Square root of gamma t, that's the speed of sound equation. Let me just list speed of sound equation to begin with. So speed of sound, of course, we know A equal to square root gamma t. Let's just derive this equation. Where does that equation come from? Okay? So speed of sound is, right now, I'm creating very obnoxious voice. Because I speak loud, intentionally, like a very obnoxious way of telling you, hey, this is something you've got to understand. Otherwise, you'll be doing kind of tone of voices. That means I constantly create this graph of disturbance, small tiny disturbance in stagnant air. Then that is going to travel, sweep through this air, and then hit in, right? Then you hear. This is the speed of sound, okay? So theoretically speaking, if I spend, I don't know, 10 hours just yelling at you over and over and over and over for 10 hours, pressure goes up, density goes up, temperature goes up in this classroom. Because every time this speed of sound sweeping through the air, well, this is quite a bit of disturbance, okay? So anyways, before and after the sweeping of speed of sound, you're going to see the slight difference in pressure, density, and temperature. Let's just find out with lots of assumptions, of course, incorporated with it. But first of all, the very beginning is, you have to change this situation to that situation. This is the real situation. Air is not moving, but the speed of sound is moving. I want to convert it to this. Well, no, speed of sound is not moving. Well, this is sound wave. Sound wave stops here, but the air is moving towards you at the speed of sound. How do you do that? From here to here. Did you do that in fluid mechanics? Did you do that in fluid mechanics? Yes. It's called Reynolds transport term, right? Okay. Early bird is flying within non-moving air, but we can never analyze anything like this. This is just a pure dynamics class. Second order partial differential equation. You never want to take that class anymore, unless you get in love with Dr. Wong. And then you dead scientist, so that means you don't want to take that class anymore. Anyways, just joking, don't take it seriously. But I want to somehow change the coordinate system so that you can analyze flow field. Okay, so now this is changed from dynamics to fluid mechanics. What is the device you employ?
Reynolds transfer.
Control volume and the Reynolds transport theorem apply to it. Okay. Now this is equivalent. Early body is not moving. Air is moving instead. Okay? So we're going to do the same thing here. So this is Reynolds transport. Okay? Change of frame. So you're going to apply Reynolds transport theorem to change the frame. Now you are dealing with non-moving sound wave. And then air is moving towards you with the speed of sound. This is the velocity. And then go across the non-moving sound wave. Then before and after, you change the property of pressure, density, temperature, right? And then you are going to employ control point. This is the control point. Okay. So obviously, this control volume has a control surface. Control surface 1, control surface 2. As you define your control volume, you're going to define control surface 1, control surface 2. This is a stream tube. Okay? Now, having said that, let's just apply a few things for this. Okay. So first thing I want to apply for this situation is, okay, what is the first thing you want to apply? In fluid mechanics, roughly speaking, we have the three conservation laws we talked about. Conservation of mass, conservation of momentum, linear momentum, conservation of energy. Which one do you want to begin with? Conservation of mass to begin with. Let's begin with conservation of mass. Okay. This is called continuity equation. Continuity equation basically says that mass flow rate across this control surface 1 must be equal to mass flow rate across this control surface 2. M dot 1 is equal to M dot 2, of course. Now, M dot 1 is density rho times velocity, in this case, speed of sound, A, right? Times cross-section area A1 must be equal to density, which is rho plus d rho times A plus dA times A2. Now, let's assume A1 equal to A2. This is the constant cross-section stream tube. Okay? So A1, A2. All right. So you can simplify this. Now this becomes rho A is equal to, rho A is equal to, this side is rho A plus A times d rho plus rho times dA plus d rho dA, right? Now d rho dA, d rho is a differential change of density. dA is a differential change of speed of sound. Small tiny change multiplied by small tiny change. What is the result? Very small body multiplied by very small body. What is that? Very, very, very small body. Let's ignore. This is 0. It's so small, I don't even care. So the result is, well, wait a minute, rho A and rho A drops out, right? Ooh, okay, this drops out. So what if, okay, so this is like A d rho is equal to minus dA. So this actually gives you A is equal to negative rho dA d rho. So this is the speed of sound. Are you convinced? So speed of sound is negatively related to the density multiplied by the ratio of the speed of sound change over density. Does it make sense? You have A right hand side, A left hand side. This is a change of A. A is depending on change of A. What is that? It doesn't make any sense to me. So this is just an intermediate point. This is not something I'm interested in. Well, I want to, well, so this is the only thing that conservation mass can tell you. It's very limited information, isn't it? And then you're not happy about it. Okay, well, conservation of mass tells you this. Okay, yeah, but, well, do we have something else? Conservation momentum, which means Euler's equation. Let's just pick up Euler's equation. Do you remember Euler's equation?
Yes.
dP is equal to minus rho B dB. Now, in this case, B is A, speed of sound. Okay? So dP is equal to minus rho A dA, right? This is Euler's equation in terms of speed of sound. Okay. So can we somehow combine this equation with equation 1? Yes, you can, I guess. Wait, not as is. I have to do something a little bit more. So starting from this Euler's equation, okay, you can say the following. You can say, well, that means dA is equal to minus dP over rho A. Oh, okay. So that means change of speed of sound is negatively related to change of pressure and change of pressure and the density and speed of sound itself. Well, speed of sound is still here, but this is equation 2. Can we combine equation 1 and 2? In other words, this dA can be plugged into here. Okay? So let's just combine conservation mass and conservation linear momentum, combining 1 and 2. You can say A is equal to minus rho. dA is what? Minus dP over rho A over d rho. Negative cancels out. This is going to be rho over d rho. dP over rho A. Rho cancels. I don't like it because left-hand side I have A, right-hand side 1 over A. Let's multiply both sides by A. That means A squared. Okay, so A squared is, oh yeah, dP d rho. Oh, okay. Oh, I see. So A squared is dP d rho. That means speed of sound square is the ratio between pressure change and density change. How much pressure change is required for the given density change is the speed of sound square. This actually indicates that speed of sound is closely linked to the compressibility, right? Higher pressure changing density, right? That's a compressibility. Somebody actually came up with a Mach number, Ernest Mach. He basically said the Mach number indicates the compressibility effects. Obviously, speed of sound is. Essentially, how much you can compress the air with a higher pressure compresses air having higher density. That's the speed of sound. So higher speed of sound means the compressibility of the fluid itself. Air comes up with certain speed, but suppose water, my goodness, what is the speed of sound of seawater? 3,000 miles per hour, something like that. That means you can never compress water. Okay, anyways, so this indicates that if you take a square root, you can somehow get the speed of sound, right? Do you think it's easy to do? So third condition comes in, okay? So we want to figure out the relationship between dP and d rho, assuming that flow is isentropic. In other words, energy principle come into play. Isentropic assumption. Question, go ahead.
Is there supposed to be an equal sign?
Equal, yeah, sorry about that. Yeah. So A is equal to, yeah. Isentropic flow, this is energy principle. Oh, 5 more minutes. So next class, if you assume that the flow field is isentropic, what's good for that? If the flow is isentropic, what's good for that?
We have the ratio of pressures to temperatures.
That's right. So you can actually use the isentropic relations. Do you remember that? So if flow is isentropic, you can basically say between 1 and 2, pressure ratio can be given by density ratio rho 2 over rho 1 to the power of gamma. and temperature ratio T2 over T1 to the power of gamma over gamma minus 1. So if the flow is isentropic, you can relate pressure and the density. Okay, that's the only chance you can finish up this equation. This is the differential equation. Somehow you want to integrate to get A. But the condition is you have to assume something. The assumption is isentropic. Because isentropic flow gives you a relationship between those two. Okay? So next class, we're going to move on to the next page saying, okay, suppose if this is isentropic, speed of sound is square root of dp d rho if this is isentropic. Okay. Question is, are you going to get square root of gamma t? Yes. So we're going to find out in next class. Okay, starting from here. Any question? Go ahead, Stephen.
So the higher the speed of sound,
Yeah.
That indicates that fluid is less compressible.
Yeah, that's right.
Okay.
Yeah, that's true. That's compressible. So water's speed of sound is 3,000 miles.
Yeah.
Air is 760 miles per hour. Right. So air is more compressible. Well, you can compress air much easier than water. That's what the speed of sound indicates. So in submarine, who is the most important person? Of course, the sonar. If somebody drop a pin in really long distance, one can pick up the sonar sound easily, instantly. It's much easier than air by hearing the sound in the water, of course. Okay. Anyways, any other question? Good for you. We're going to see you on Wednesday. So continue working on your quiz 0. Quiz 5 is coming up. See you on Wednesday.
So it's going for the project. I'm actually not gonna do the class project.